Can you hear me?
Yes.
Yes, we can.
Yes, sir, we
Very
can.
good.
We just wait a few more minutes for the students to join.
Okay. Are you able to see my charts?
Yes, sir.
Yes, but your screen
you
is
can make-
visible.
You can make it full screen. Yes.
Yeah. Now.
Everything is
Okay now.
okay?
Yes.
Yeah.
Okay. Somebody will let me know when to start talking.
Yes, sure, sir.
Is the volume of my sound okay?
Yes, it's fine.
Okay, very good. Does anybody have a comment from yesterday while we are waiting to start?
I think Akansha will let us know.
None, nobody has any comment. Maybe we can start and students can join in, keep joining in. Actually, they will keep joining in. So maybe I'll just introduce the speaker again. So Professor Virendra N Mahajan, he's going to continue his lecture series and talk about axial irradiance of a focused beam today. So over to you, sir. You may start your talk. I would
Okay.
just highlight, yes. So the questions can be asked in the middle of the talk. You can just post your questions to the chat box or unmute yourself and ask the question.
Yeah, my preference would be you ask me the question when it comes to your mind, and you don't have to put it in the chat box. I wouldn't know how to use it maybe, but so it's okay for me to start.
Yes, sir. You can start.
Okay, very good. We're going to discuss this, as the title says, axial irradiance of a focused beam. And just as a preamble, you would expect when you focus a beam of light that the brightest point would be where the focus is, the focal point. And these are the topics we are going to discuss. We'll very quickly review the point spread function. You might keep in mind, of course, when you focus a beam in the focal plane, you will observe the Airy pattern if the beam being focused is aberration free. And we are going to, instead of looking at the two-dimensional distribution in an image plane, we will be focused on the axial irradiance. And we introduced the notion of Strel ratio yesterday, and we'll talk about it one more time, and maybe two more times as the time goes. And we are going to be, since we are going to focus on the axial irradiance, that means we will take a detector in hand and walk along the axis of the beam with that detector and see how the axial irradiance varies. And if we are walking along the axis, that means we are going out of focus and from the focal point. And we will write the defocus aberration in terms of the Fresnel number of the beam. And we'll talk about what a Fresnel number is and how we calculate and write the defocus aberration in terms of the Fresnel number. And we'll talk about beams with the small Fresnel numbers and large Fresnel numbers. And we want to see what happens depending on the large or small Fresnel number on the axial irradiance. And we'll find some interesting results. In particular, in general, we would expect the brightest point to be at the focal point, as we said earlier, but we'll see how it in fact varies. as we go out of focus along the axis of the beam. Now, this is the equation we wrote in some fashion yesterday. P is the pupil function. It has the amplitude as well as the phase aberration, which is in the exponent, and then the Fourier transform of that pupil function, modular squared, inverse square law, R squared, and dependence on the wavelength also as the inverse square. Meaning smaller the wavelength, smaller the size of the airy disk as an example. And it's in 2 dimensions, so effect of lambda is also as lambda square. And if we assume a uniformly illuminated circular pupil, and if it is uniform, aberration free, pupil function is constant, comes out of the integral, and this integral reduces to the 0-order Bessel function, which we integrate across the pupil with the radial coordinate rho, and this is the airy pattern we talked about. And I mentioned yesterday that when Airy derived what we call the Airy pattern, he wrote the expression in terms of an integral. He apparently did not know the Bessel functions at that time when he wrote that paper, even though the Bessel functions had been written papers on by Bessel about 17 years earlier. And the paper Airy wrote is in 1835, and we gave the reference to the paper by Rayleigh, which gives how much light is contained in a circle of some radius. Airy disk, we said, contained almost 84% of the light. And this is what we had mentioned yesterday. And we also mentioned that the aberrations, Airy pattern, mind you, is for the aberration-free case, no aberration, spherical wave coming out of the exit pupil. If the beam is aberrated, the central value goes down, and we said qualitative reason is that the Huygens secondary wavelets that originate on the spherical wavefront, now which is aberrated, therefore they are not in phase, and there is some non-constructive interference, therefore the value goes down at the center. How much the value goes down? That ratio, the aberrated value divided by the aberration-free value, is what is called the Strel ratio. Strel wrote his paper trying to explain how the value will go down. A simple expression, an empirical expression, is the Strel ratio equal to e to the minus sigma square. Sigma square is the phase variance of the aberration. Phase variance is written here, mean of the square of the phase aberration function minus square of the mean. By definition, that's what variance is. And from this simple expression, you can show that for a Strel ratio of 0.8, meaning a 20% reduction in the central value, the standard deviation of the aberration is approximately lambda over 14. And it is independent of the type of the aberration, meaning whether it's spherical aberration, defocus, astigmatism, coma, higher orders, whatever. As long as the aberration is relatively small, the Strel ratio of 0.8 is obtained when the sigma value, the aberration value in terms of its standard deviation, lambda over 14. And this simple expression is written in long ago now, 1983, and we are now in 23. Our focus today, tonight, for me, morning for you, is how the axial irradiance varies as a function of the distance. We have a spherical wave coming out of the exit pupil. Its center of curvature is at the, say, Gaussian image point, given a point source on the object plane. And very easy to go on the wrong side. We are interested in the axial irradiance. We will make an observation at a distance z, given that the beam is focused at a distance r. Z and r being different from each other means there is a longitudinal defocus, z minus r, and corresponding defocus aberration. And the defocus aberration, which is r square, where r is the radial distance of a point in the plane of the exit pupil, is given by this expression: difference in sags of two spheres, one with radius of curvature r and the other with radius of curvature z. And there are higher order terms which are continuously smaller and smaller, but this is the defocus aberration. And we use the normalized radial variable rho varying from 0 to 1, and we write it in terms of b sub d rho square, where b sub d is this, a being the radius of the exit pupil. And in terms of the phase aberration, we multiply by 2 pi over lambda and write it in this expression. And we are going to write this defocus phase aberration in terms of the Fresnel number of the beam as observed from the focus in terms of the so-called Fresnel half-wave zones in the circular pupil of radius A. So here is the exit pupil shown of radius A. R is the distance at which the beam is focused at, center of curvature of the spherical wavefront. And let there be n half-wave zones of Fresnel. That is this diagonal distance. And we can calculate what this Fresnel number is. Diagonal distance equal to r square plus a square. And with the quadratic term in lambda square being negligibly small, we get this expression, which gives n, the Fresnel number, equal to a square over lambda r. And we write our defocus aberration in terms of the Fresnel number in this form: b sub d equal to pi n r over z minus 1. Now, if you look at that expression, it tells you if the Fresnel number is large, then z and r cannot be too different from each other. They must be very close to each other if the Fresnel number is large, because otherwise the amount of defocus may be considerably large, that the image that you might obtain if it was an extended object, it'll be very blurry, totally out of focus. So large Fresnel number gives small depth of focus, just based on looking at this expression. Depth of focus meaning how much out of focus can the beam be, and still give a reasonably good, let's say, the aberrated airy pattern, defocused airy pattern, or for an extended object, the extended image. And this is the case in the case of a photographic camera, which we'll consider a numerical example of to get some idea. what is a large Fresnel number, what is a small depth of focus in that case. And similarly, if the Fresnel number is very small, the depth of focus can be very large, as in the case of a laser transmitter. You have a laser beam and you are focusing it on a target at a distance, whatever, typically large, and we want to determine what is the depth of focus in such a case. Such a case meaning small Fresnel number. The defocused PSF is given by this expression, where B sub D, the defocus aberration, is shown here, and that is in radians. So we don't have to carry the 2 pi over lambda factor. And if B is 0, obviously this J0 Bessel function, when integrated over the radial coordinate rho in the plane of the pupil, yields this the Airy pattern if it is aberration free. And the reference for this work that I'm going to be discussing is in 2005. I showed these defocused PSFs yesterday. This is just a repeat. And in particular, depending on the amount of aberration, and if it is integral number of waves, the Strahl ratio would be 0 at the center, dark spot. Now, we are going to be a little bit more careful because we are going to discuss the depth of focus. Therefore, the effect of inverse square law we are going to include in our discussion. So, because of the inverse square law dependence on the distance z, we sort of redefine the Strahl ratio. Strahl ratio is axial radiance at a distance z when a beam is focused at a distance r. So if the beam is focused at a distance r, observation is being made at a distance z, that means we are out of focus making the observation. And divided by the axial radiance at a distance z, beam is also focused at a distance z. Obviously, at a distance z, beam being focused at z should give the maximum irradiance, at least in terms of the defocus aberration. Beam is perfectly focused here, beam is not perfectly focused here. And the Strahl ratio will be less than or equal to 1. This can be shown analytically based on Schwarz inequality and other inequalities of the kind. So in defining the Strahl ratio, we are considering only the effect of defocus as an aberration. The inverse square law effect is the same both in the numerator and the denominator, because in both cases, the observation is being made at a distance z. So only the effect of the aberration is considered in defining this Strahl ratio. And we have said earlier, in the case of defocus aberration, which is what we are considering, at least at the moment, the Strahl ratio can be as small as 0. Now, if you let r equal to 0, meaning along the axis, you can show that that integral can be carried out in closed form, and this is the expression that you obtain. Very simple expression. R over z square, that represents the effect of inverse square law, and sine b over 2 divided by b over 2 thing square. This is where the defocus aberration is. So, and this expression giving the axial irradiance is in units of the focal point irradiance. Focal point irradiance is total power times the area of the exit pupil divided by lambda square, and r square. That's the focal point irradiance. So it's written in those units. So looking at the axial irradiance, you notice it depends on two competing factors. There is increase due to inverse square law if z is less than r. If z is less than r, this number will be larger than 1, and therefore the irradiance will increase at a certain distance z, only because of the inverse square law dependence. And this can be significant only for large depth of focus or small Fresnel number n. Otherwise, z will be very nearly equal to r, and therefore the impact of the inverse square law would be negligible, meaning it'll be relatively constant within that small depth of focus. A decrease due to defocus aberration, non-constructive interference of Huygens spherical wavelets, and that, of course, has its own impact. Sin x over x square is a number smaller than 1, and it's only going to decrease as we go out of focus. So axial irradiance closer to the pupil can be higher than the focal point irradiance if the increase due to the inverse square law is higher than the decrease due to the defocus aberration. And that is a point that you need to keep your focus on. Meaning, although in general, we would say the brightest point along the axis would be the focal point. But here we are arguing the irradiance along the axis, meaning going out of focus, in principle can be larger if the effect of inverse square law, meaning for z less than r, would be, I'm sorry. Please forgive me. So I would like you to anticipate that depending on, in particular, in terms of the Fresnel number, depending on its value, giving small or large depth of focus, the axial irradiance can be higher than the focal point irradiance. And in fact, I show here axial irradiance for different values of Fresnel number n. I'm using simply that expression, r over z square times sine b sub d over 2 divided by b sub d over 2 square. Just using that expression, if n equals 1 or 10 or 100, how does the axial irradiance vary? And back to the page I want to be at. This solid curve is the axial irradiance for Fresnel number 1, meaning there is only one Fresnel zone in the exit pupil as observed from the focal point. And you see how the axial irradiance varies. This is the focal point, z equal to r, z less than r, and of course, in this range, z greater than r. So you can see when n equals 1, the peak value occurs at 0.6 r. That's written here. And it corresponds to defocus wave aberration of lambda over 3. The Strel ratio is 0.68, if you substitute B sub D equal to lambda over 3 times 2 pi over lambda, so that is phase aberration. And here is the inverse square law, R over Z sub P, peak value, Z value for the peak is 0.6. And therefore, this factor is 2.78. 2.78 times 0.68 is obviously a number larger than 1, and in fact, close to about 2. The peak value is twice as much as the focal point value. If n equals 10, we are increasing the number of half-wave zones in the exit pupil. The focus is here, and peak is also roughly there, but not exactly. And as n becomes larger, in this case 100, the pattern, axial irradiance pattern, is symmetrical about the focus. On either side, if you go a certain distance, you get the same value. Whereas otherwise, when Fresnel number is small, it is asymmetrical, and of course, smaller it gets, the asymmetry increases. And of course, as you approach the Z value where the exit pupil is, well, that will be the pupil irradiance, and so on. So what I have tried to show here is that indeed the depth of focus is very large, smaller the Fresnel number. Now you might think, is n equal to 1 real? Yes, it is real. N equal to 0 is a parallel beam, plane parallel beam. And the question we may want to ask ourselves is, if our goal is to get the brightest illumination on a target, given the parameters of the system, where the Fresnel number may be in fact small, where should the beam be focused at? And that's a question I ask on the next page. So first of all, I want to make sure that you understand and agree that the value of axial irradiance, and corresponding to the whole pattern, but the central value, which is the axial value, can be large, can be significantly larger than the focal point value. And so I ask the question, what is the optimum focusing on a target at a given distance Z? Say we have a target which we want to heat up, perhaps burn, and question we ask ourselves, given the parameters of the system, parameters of the problem, where should the beam be focused at? And I would like you to think about what answer you come up with. Should we focus beyond the target, on the target, or inside the target? Inside meaning at a shorter distance than where the target is. Anybody who would like to volunteer? Where should the beam be focused at? Are you listening to me? Anybody?
We are listening. Yes. Okay.
I'm hoping a student would say something about. Where should I focus the beam? Well, it's obvious that I shouldn't quite focus on the target. Is it obvious? Shouldn't I focus at a point where the peak value of the beam is on axis? I said when n equals 1, the value at the center is roughly twice as much at a distance of 60% of the target distance. Should I focus there? Well, let me give you the answer. Since the target distance is fixed, it is at a distance z. And all I want to know is what should the value of r be if I have control on focusing the beam. And let's assume I have a system where I can easily focus the beam at whatever distance I want. Now, target is at a certain distance, 1 kilometer. It's not changing. I just want to know where to focus the beam so that the illumination on the target will be maximum. That's the question I'm trying to ask. Now, since inverse square law dependence is fixed, no matter where I focus, my observation distance is still z. Therefore, if I focus the beam somewhere else, I'm only going to introduce defocus aberration. And defocus aberration is only going to reduce the illumination at the center. So I have given the answer. Do you get it? Do you understand it? Do you agree with it? There were two factors we said, inverse square law dependence and the defocus aberration dependence. Inverse square law dependence is fixed because my target distance is fixed. And aberrations, meaning going out of focus, defocus as an aberration, will only reduce the value. Therefore, I must focus my beam where the target is, even though a higher value will occur at a distance shorter than the target distance. But there is not a reason to focus the beam at a shorter distance, because I still want the illumination to be maximum on the target itself. So the answer is accordingly, a beam focused on the target yields maximum central irradiance on it, even though a larger value occurs closer to the pupil when n is small. And if you have any doubt, we can check it. So that's what I do on the next chart. Central irradiance on a target. Now, my distance z is fixed. R as to the distance where I focus the beam at is the variable. So it's R over Z, not Z over R. And as I vary R, keeping Z fixed, depending on the value of n sub Z. N sub Z is the number, Fresnel number observed from the distance Z. Fresnel number of the pupil observed from a distance Z. And you see the peak of the illumination lies when R equals Z. Otherwise, it goes down. Is that clear? You may want to know what is I sub U and what is I sub G. Well, I sub U is for a uniform amplitude beam. I sub G is if it's a Gaussian beam with, I say here, gamma equal to 1. That means the amplitude goes down to 1 over E at the edge of the pupil compared to the amplitude at the center. Obviously, a Gaussian beam has a certain size, large, small, whatever. It has a value of unity at the center, let's say, and it decreases as you move outward on the pupil distance. 1/e when it is at the edge of the pupil, that's the result. You obtain this dashed curve. So all I want to say is if you had a Gaussian beam instead of a uniform beam, you'll get a similar result. Details would be different, but the result would be similar. Similarly, n sub z equal to 10, you notice it is not quite symmetrical, but when n sub z is large, now it is symmetrical. So target at a fixed distance z from the plane of the pupil, that's where my device is, where I'm able to focus at whatever distance I choose to. And the beam is focused at various distances r. N sub z is now a square over lambda z, represents the Fresnel number of the pupil, as I said, as observed from the target distance z. And in each case, the peak value occurs at r equal to z. So the reason we are obtaining this result is in most cases of imaging, the depth of focus is very small. And therefore, z is practically equal to r. The difference cannot be very large, otherwise the image will be blurry. And therefore, we never come across a situation where the Fresnel number is small. So let's continue. Photographic camera. I just picked some numbers. The diameter of the exit pupil is 2 centimeters. The film, as in the old days of a camera, not in your smartphones, the film is at a distance 10 centimeter. Now you will put your chip at that distance. And again, I'm assuming, let's say green light, lambda equal to 0.5, although in practice, it'll be white light. And the Fresnel number is 2000, a square over lambda r. Fresnel number is obviously very large. And a Strel ratio of 0.8 is obtained when B equals a quarter wave, plus side or minus side. I mean, in the old days, when you were holding your camera, you were turning the knob and focusing it and so on. These days, and for many years now, focusing is done automatically. The camera looks at the object and maximizes something, and automatically and relatively instantaneously focuses the lens onto the object to give a decent image. And the depth of focus is 25 micrometers. So if my distance is 10 centimeters, 25 micrometers, Z and R are very nearly equal to each other. Not exactly, but practically equal to each other. The depth of focus is so small that there is a negligible impact of the inverse square law dependence in the narrow region of interest. Narrow region of interest meaning within the depth of focus. Any question? Comment? You can say, you're not surprised, you are surprised, or big deal, whatever comes to your mind. Any comment?
is it only for narrow region of interest, or can we also apply it on like big areas?
Well, it doesn't have to big area, meaning in the object plane or in the system that you are imaging.
In
I
the
mean,
object.
if D is 2 centimeter, it could be 20 centimeter. Ultimately, you have to figure out what is the Fresnel number, and therefore, what is the depth of focus.
Oh, okay.
In a photographic camera, depth of focus is very small. Inverse square law dependence is fixed. It doesn't change. If you try to go out of focus quite a bit, image would be blurry. Obviously, you are not interested in that. So from a practical point of view, the impact of inverse square law variation is negligible.
Okay, sir.
And therefore, the Z over R square that we have written, or R over Z square, is fixed. It's only the sine square that we talked about. I should not say sine square. It's called sine x over x is sometimes called sig squared. It's only the impact of that. And that number is always less than or equal to 1. And therefore, the tolerance for the longitudinal defocus, which is Z minus R, is very small. Any other question before I talk about laser transmitter? Any question? Okay, let me continue. Let's consider a laser transmitter. Here I cooked up a problem, D equal to 25 centimeters. I have a laser beam, which is 25 centimeters. Typically, laser beams that you deal with in the lab, etc., they are small. But this is a device that I'm going to use to burn a target. Target is roughly at 1.5 kilometers. That could be the distance of a tank in the case of a war situation. And I'm using lambda equal to 10.6 micrometer. This is CO2 laser. Now, I just chose those numbers so that N will come out to be 1. B sub D is this expression. And a stir ratio of 0.8 is obtained for Z lying between 1 kilometer and 3 kilometers. You see how large the depth of focus is? Whether I focus at 2 kilometers, 1.5 kilometers, up to within 1 to 3, my stir ratio is 0.8, which is very high. So I hope you realize that depending on the system you are dealing with, when I say system, I mean the optical system, the depth of focus can be very small or also can be very large, depending on the device you're using for the application at hand. So the defocus aberration becomes significant only when Z is much different from R. And the principal maximum lies at 0.6 R, 0.88 kilometer. But the maximum irradiance is still obtained at the distance R, which is where your target is. That's where you want maximum illumination. And there's same factor of 1.9. Is it okay so far before I take the next step? It's only going to get a little bit more complicated.
Yes, sir, you may proceed.
Is there a comment, question? Okay, let me continue. Now, knowing how the axial irradiance of an aberration-free beam varies, we want to know what the effect of an aberration might be. Now, keep in mind carefully when I say aberration-free beam. The beam is aberration-free only when the observation is made at a distance r, meaning the focal point. At any other distance, although there is a spherical wave and therefore spherical wavefront coming out of the exit pupil, it is defocused as soon as we make an observation at a distance other than r, distance z, compared to r, where the focal point is. That's very important to keep in mind. I repeat, the beam is aberration-free only when the observation is made at a distance r. In fact, if it is, in fact, aberration-free, we observe the Airy pattern. At any other distance, we know the central value goes down because of the defocus aberration, because of making observation in an out of focus plane. Even though the wavefront is still spherical coming out of the exit pupil. But precisely because we make the observation in a plane other than the focal plane other than at a distance r, the beam is not aberration-free. That's something to keep in mind. Okay. Now, we want to, for example, make the observation in whatever plane we choose to, but let's say the beam happens to be aberrated in addition to the observation being made in a plane out of focus. And in particular, we'll consider, suppose spherical aberration is what the beam is aberrated by, or astigmatism is the aberration in the beam. What happens then? Any anticipation? We said, without making too much noise about, that aberrations can only reduce the central value. Now, I'm starting with a perfect beam, spherical wavefront, and I have studied how the axial irradiance varies. On this page, on this chart, I'm going to introduce spherical aberration in that beam. And I would normally expect, oh, if I introduce aberration, the central value should go down. And I'm going to show not necessarily. It can, in fact, go up. So, large Fresnel number axial irradiance is of interest in the vicinity of focus due to small depth of focus. Aberration reduces the central radius. If it's a small Fresnel number, axial irradiance is larger at points closer to the focusing pupil. Since the depth of focus is very large, inverse square law effect takes over. The increase due to inverse square law is higher than the decrease due to the defocus aberration. Now, I'm going to, some authors considered axial irradiance of a Gaussian beam and remarked that the increase in axial irradiance, the increase in axial irradiance due to spherical aberration was beyond the diffraction limit. Meaning, they took a perfect beam, calculated the axial irradiance, and then introduced spherical aberration in that beam, and they found, oh, axial irradiance goes up in certain places, in certain range. And they are surprised, and they remark, oh, this is really beyond the diffraction limit. And I give the reference here, these two Japanese authors. And some of you may even know Asakura. He may have visited IIT Delhi in earlier years. This paper from '96. And other authors working with a uniform beam instead of a Gaussian beam have remarked that the increase in the presence of spherical aberration is unexpected, meaning you don't think it should be, but happens to increase. And in both cases, they are considering small Fresnel numbers. And they wrote their paper in '97, roughly around the same time. If you look at what month they published, these are two Europeans, and these two are Japanese. However, now it's my turn. However, these results are neither beyond the diffraction limit nor unexpected. So what is it? They are a consequence of balancing of defocus aberration with spherical aberration. What has happened is, in the absence of spherical aberration, there was defocus aberration, if you are making the observation in a plane other than the focal plane. You introduce spherical aberration, the right amount, the right kind, meaning minus sign, if you remember from yesterday. The combination of the two, defocus aberration and spherical aberration, they can reduce the value of the standard deviation of the combined aberration. And if the standard deviation goes down, Strell ratio is going to go up. And that is why what they thought was beyond diffraction limit or unexpected was in fact a simple case of defocus aberration being balanced with spherical aberration to reduce the standard deviation of the combined aberration. And that's why I was focusing earlier. A focused beam is aberration-free if its wavefront at the pupil is spherical with its center of curvature at the focal point. That's the only place it is aberration-free. But a beam observed at a plane other than the focal plane is no longer aberration-free. It is in fact aberrated by the defocus aberration. Spherical aberration or astigmatism balances the defocus aberration, reduces the aberration variance, and thereby increases the Strell ratio, and therefore the irradiance at the center. And here I show by how much the standard deviation is reduced. Defocus aberration is here a result of making observation in an out of focus plane. I am going to add some aberration to it and calculate what the standard deviation is. If it's only defocus, standard deviation is given by this expression, b divided by 3.46. The exact number is 2 times square root of 3. And if I balance it with spherical aberration, and I'm going to balance it to minimize the standard deviation of the combined aberration, the amount of spherical aberration I must use is minus 15/16, almost 1 here, but not quite, the amount of defocus aberration. And now the standard deviation has reduced by a factor of 4. And if you balance defocus aberration with astigmatism, this is the expression for astigmatism, rho square cosine square. And if you choose the coefficient of astigmatism to be minus 2/3 of B, you get the minimum sigma value. From 3.46 here, it's a larger number. The reduction is not as much, but it is still reduced. And as long as it is reduced, the Strahl ratio will go up. And here I show the result again for small Fresnel number, n equal to 1. Gamma equal to 0 means it's a uniform beam, not a Gaussian beam. I'm sorry. Okay. If there is no, let me go back. I don't know how to control myself. Just a moment, please. Okay, this is with spherical aberration. If there is no spherical aberration, this is this axial irradiance curve, which I showed earlier. If you balance it with the spherical aberration of, this should be 15/16 lambda, this is the curve. Oh, here is an example of 5/16. This is the curve. And you see this, the focal point is over here. Z/R equal to 1. And the value is higher and becomes even higher yet when you introduce aberration into the beam. And if you continuously choose the optimal value of spherical aberration so that the standard deviation is always minimized, this is the curve. And you can see these results are quite different from what it would be for a focused beam, aberration free, with a Fresnel number of 1. This is the case with the astigmatism, similar results. This additional curve here is showing what the defocus aberration is as you move from the focal plane to out of focus. And I'm ready to make conclusions, assuming, I hope, you find the briefing interesting. You may have to think about it a little bit, etc., what I have discussed, but here are my conclusions. Maximum of irradiance in the focal plane of an aberration-free beam occurs at the focal point because that's where the Huygens secondary wavelets interfere constructively. Aberrations reduce the central irradiance, yielding Strahl ratio less than or equal to 1 because the Huygens secondary wavelets are not in phase and therefore they interfere non-constructively. There is some partial destruction. Now, depth of focus is small for beams with large Fresnel numbers, as in the case of a photographic camera, or the depth of focus large with very small Fresnel numbers, as in the case of a laser transmitter I indicated. Now, for beams with small Fresnel numbers, the maximum of axial irradiance lies at a point that is closer to the focusing pupil, because the increase due to inverse square law is larger than the decrease due to the defocus aberration. And axial irradiance is at its maximum and its vicinity. It increases when an aberration is introduced. And we gave the examples of spherical aberration and astigmatism, and therefore there should be no surprise. My thinking at the time was, when I saw those papers by the two Japanese and the Europeans, that they were probably physics major type, not the classical optics type like I am. But there is a real answer, not to talk about, beyond the diffraction limit and so on. Diffraction limit simply means that the imaging is aberration free. But how the aberrations impact, there can be surprises, as I have tried to indicate here. This is my last chart. I didn't have it last night. All this thing that I have discussed is, you can look at the details in this part 2 of my book on optical imaging and aberrations. This is the second edition, and I hope you appreciate what I'm trying to show here in this figure on the book cover. S here, the dashed curve, is a spherical wavefront. This W here is the actual wavefront. And the gap between the two along the rays represent the aberrations. And this is an observation plane. It could be, in fact, the Gaussian image plane. And I'm showing a case where the aberration is comma, and that is the Airy pattern aberrated by comma, and so on. That's all I have. Please feel free to comment, ask any question, and so on.
Kehar Singh here.
Yes, sir.
I'd like to make a remark
Please do.
for the mainly for the benefit of young students. See, whatever Professor Mahajan has discussed is based on the scalar theory of optics. Now, it so happens that for large numerical apertures, let's say beyond 0.50 or so, taking a rough value, the scalar theory breaks down, and one has to use the vector theory, taking into account the polarization state of the incident light. And many a times I have seen that or most of the time I have seen that the students apply the scalar theory blindly, irrespective of the numerical aperture of the system. For example, the Airy pattern, they calculate this for any value of the numerical aperture, but beyond 5 it gives absolutely wrong results. So they have to use the Debye-Wolf integral, and Hopkins was the first one to give a detailed theory way back in, I think, 1949 in a small note, and then in 51 in a detailed paper. Now the problem arises because at MSc and even at MTech level, we teach them only the scalar theory of diffraction, which results in well-known Fresnel-Kirchhoff diffraction integral. But it has to be applied very cautiously. Now, in your case, I do not know whether n is equal to 1 corresponds to, I mean, for a typical case, for example, what does n correspond to? And Fresnel number.
Well, as I said, n equal to 0 is a parallel beam. There's no problem with numerical aperture and the like.
No, I'm talking about the focusing, the numerical aperture in the image plane. So even if you have a parallel beam of light and you are very close to the pupil function or very close to the image forming system, such that the numerical aperture in the image space goes beyond 0.5, let's say, supposing it's 0.9, which means you are very, very close to the system. Scalar theory breaks down.
It is the angle that the wave makes at the focal point, and how
Yeah,
fast
angle
it is.
decides the numerical aperture.
Yeah, but the example I made up, the distance at 1 kilometer, the aperture 25 centimeters. That
will not qualify.
And 25 centimeters. It's not entering into that zone at all.
That's very high. That's very high number. N will be very high, right?
The focal ratio is
No, n will be low.
How low?
I mean, it is. See, when only n equal to 1, that means the radius is very, very small. Aperture is very small as compared to the distance.
compared to the range where
The
you're
range, yeah.
making the observation.
Yeah.
Yeah, if it is very low, then of course scalar theory is valid.
Yeah. So it is n. When n is large, then the vector theory will come into the play.
Not necessarily.
From the angle of the marginal.
We calculate. I'm sorry.
Yeah. The angle of the marginal ray would be very, very high. I mean, that is the kind of thing.
I mean, if the range was very small, comparable to the diameter of the beam, only then would you have to worry about.
Yeah, in that case, n would be very large.
Yeah. But we are considering a range to be in the photographic camera as well as here. The focal ratio is such, the distance is long, the diameter of the aperture is small. But your point is well taken. That
yeah, of course, I was talking about cases where the radius of the aperture or the optical system, or for that matter diameter, is large as compared to the distance at which you are making the observation.
Right, I understand.
Which means marginal ray makes a very large angle with the axis. So for numerical aperture, I know that when it's less than 0.5, scalar theory can be applied. Beyond this, it breaks down.
Actually, wherever the paraxial theory is applicable, paraxial can be scalar. You know, all this Fresnel, Kirchhoff integral, they are all paraxial. They are all paraxial.
Yes. Oh, sure.
Yeah. So whenever you go much beyond paraxial, then the angles becomes very large, and then in fact the concept of transverse component becomes, and you have a significant longitudinal component, and that is where the vector enters.
In your seasoned professors, in your teachings there, did you discuss this in the class at all? Giving a lecture?
No, vector theory is never taught.
Yeah, it's hardly. It is just mentioned at all.
It's just mentioned. Mentioned, as Professor Sharma said.
As a limitation.
As a limitation. That one should be cautious.
Understand. Yeah, I have not dealt with in my experience
but
either.
That is small. But that small caution is lost in the mathematics that you know.
Right, understand. I mean, all my books.
They don't remember that.
I never dealt with it. At work, I never dealt with it, and so on. I didn't have to, that is.
Yeah, I know. All your books are based on scalar theory.
And in most
Or research
applications, that's
papers
all
for
you
that.
need.
Yeah.
Actually, these things become important. For example, if you are doing in the nonlinear optics a Z-scan method, where and then you have a very highly focused beam,
Yeah.
then these things become very important. But then the
Yeah.
actual electric field becomes important.
Yeah.
Then it becomes very, very
Actually, the simplest system is a high resolution microscope. The numerical aperture is very, very high.
Yeah, in all
Numerical
my
aperture
work,
of 0.8, 0.9 is not uncommon.
yeah.
understand, I was going to just say, in all my work,
And
I never
here
had
the-
to deal with polarization,
yeah.
and I never had
And-
to deal with anything other than what I
And
have
in that
discussed.
case, one of the qualitative results is that airy pattern is no longer circularly symmetric. It becomes elliptical in shape.
Okay.
That is a simple
Anybody have
result.
any comment?
Apart from other distributions and central intensity, encircled energy, OTF, everything changes.
Anybody else has a comment, question, students? I might mention that you guys, all of you come fresh in the morning to listen to me. For me, it is time to go to bed, although I don't go to bed that early. But I have enjoyed giving these two talks. I hope some students will want to know a little bit more about what I have discussed. I hope it has been interesting to listen and so on. And I wish I could have come